Okay, this is the fourth problem, 2005, number 3. Sorry, the copy quality is not very good. I'll blow this up a little bit so you can see it. Oh, not at all. So it's 2q down at the bottom, and then if you look at the top, it's just a plus q. So it says 2-point charges are fixed on the y-axis at the location shown in the figure above. A charge of plus q is at plus a, and a charge of plus 2q is located at minus a. Express your answers to parts A and B in terms of q, a, and fundamental constants. Still, as always, remembering that a fundamental constant is k, so you can have that in there. Determine the magnitude and direction of the electric field at the origin. Well, if you remember your equation for an electric field, that's basically what it is. And the electric field is summative, which means if you have two particles causing this field, you just do that twice. So we'll start here. So the first one is k, which is okay. The q we're allowed to use is a lowercase q, and the distance between it is a distance of a plus k, and in this case it's a 2q at a distance of minus a squared. So when you run this whole thing through, mathematically, you got to make sure of a couple little things. First off, that is going to go away because that's a square. And second off, you have to remember that the field due to this is down, and the field due to this is up. So they're in opposite directions. So don't forget to take care of that. And depending on which one you made positive, actually, I think the answer key, yeah, I think the answer key makes the 1q negative. So when you go through it, you get 2 minus 1, and all you end up with is kq over a squared. Okay, so there's part A. Part B says, determine the electric potential at the origin. Well, the electric potential is also a summative thing. So basically, if there's 1, you just have 1. If there's 2, you have 2. If there's 3, you add 3. And that's all you do. Remembering that your equation for potential is just kq over r. And now you simply plug in what you've got. So the k stays the same. So for the first one, it is kq, it's just a plus q here over a distance a, so it's just kq over a. Nope, not equals. kq over a. And then we have to add the second one, which is just 2 kq over a. Once again, the distances are the same, so you add them up and you end up with 3 kq over a. Just that easy. Because they were both positive charges. All right, now we get into a little bit of the meaner stuff. And I only say meaner just because it looks a little nastier. So first off, we need the distance between these two charges. It'll be the same here also, so let's not worry about both of them. Let's just get one, and if we need to use it again, we will. And we'll call that r. My distance is simply going to be, let's see here, square root of x naught squared plus a squared. And that's just a Pythagorean theorem. This is a squared plus b squared equals c squared. Take the square root of both sides, and there you go. So for the plus q charge, which is right up here, F is equal to k q1 q2 over r squared. So plugging in what we know, I know I can keep my k. I've got a plus q and a minus q, but remember in this problem we use the absolute value, so it's just q times q, so it's just q squared, and then the distance between them squared, which is just x naught squared plus a squared. The square root falls away because of the square up here. Okay, so there's part 1. Now for part 2, it's going to be strikingly similar. In fact, the only thing that's going to change is that right there. Because the distance between the charges is the same. The only value that changes, at this time it was q, and the second time it's 2q. Okay? All right, part D, the final part, gives you a graph. Now, these graphs can be good or they can be bad, but they're usually worth a considerable amount of points, so they're worth taking your time on. So D says the minus q charge can also be placed at other points on the x-axis. At each of the labeled points A, B, and C on the following diagram, draw a vector to represent the direction of the net force on the minus q charge due to the other two charges when it is at those points. So if I took a big old fat minus q charge, let's see what we can do with this. Nope. There we go. Shrink it down here. Oh, not that small. Too small. Too big. Perfect. And I put it at point A. You should be able to see at point A that it'll be attracted this way, but it'll be more attracted that way. So if you add these two vectors up, you end up with a net attraction that is like right there, in between them. So at section B, now we stick the charge there, you can see that the net force will simply be down, because the bottom positive charge is better. And then we scoot along to C, and the same thing is going to apply here. The only difference is the angle should be a little bit steeper, but it doesn't look like they took off any points if it wasn't, but it's still going to be attracted down there. Okay, that was the fourth problem.